we are at the Indian Brook portable water plant, water filtration plant, and we're here with Andy Teese and Paul Frioli to go over some of the intricate parts of this water filtration plant so that all the people out there understand what goes into making your drinking water as good as it is. We have exceptional drinking water, and here we are standing on top of our dam, our newly constructed dam, and I'm going to let Paul Frioli tell you a little bit about it. Paul?
Thank you, Sue. What we thought would be a good idea was to start our tour of this facility at our most precious natural resource in the village, and that would be the Indian Brook Reservoir. If you pan behind where we're standing here, you could see the Indian Brook Reservoir, which is fed by the Indian Brook and whose watershed is mainly consists of the T-Town area in the town of Ossining and Newcastle. The reservoir presently holds, at full capacity, approximately 100 million gallons of raw water for us to utilize as one of our sources for our Indian Brook water filtration plant that we are going to tour today. The other resource that we use is Croton Reservoir, New York City Croton Reservoir raw water that is fed to us through the old Croton Aqueduct. We'll look at that later on our tour today, but right now we wanted to start at our Indian Brook Reservoir on top of our earthen dam. The earthen dam, again, if you pan to the left here, holds back the 100 million gallons, and the main component of this project was the reconstruction of the spillway. That's what necessitated the project, and we're going to walk over there next to talk a little bit about that.
As you can see behind us is the Indian Brook Reservoir and this beautiful scenery that we have here in Ossining that's part of this. It's very important that we understand all of the aspects of this so that we can move on and find out what we need to do as a community to make this all better. So now we have walked across the earthen dam and we're here at the spillway, and we're going to have Paul continue to tell us about the different weir chambers. Are they weir chambers? So very similar to what we have in the aqueduct when you can go next door to the community center and go down the weir chamber. This is a modern weir chamber.
Thank you, Sue. So again, as Sue mentioned, here we are at the weirs that are the beginning of the spillway, and if you pan to the left with the camera, you can see the channel of the spillway that works its way all the way down to the right of the air structure there, and eventually out to the Croton River. The spillway is really designed in an earthen dam to protect the earthen dam from being inundated during a high rain situation where the water would be allowed to flow out of the spillway in a flooding condition versus overtopping the earthen dam and compromising the structural integrity of the dam. So right now you can see that the water is just below the elevation that would allow it to overflow and go out into the Croton River, and we keep it there because we want to maximize our natural resource and we don't want to waste any of it. The only time we would ever want to see water flowing over the weir is if we had to protect the structural integrity of the earthen dam. So right now, the 100 million gallons that is in here is kept at that elevation, and we draw from it approximately anywhere, depending on the quality of the intake of the raw water, anywhere between 1 and 3 million gallons to feed the filter plant down below. And what I want you to do is pan around the reservoir about 180 degrees and go all the way back to those docks that we walked past. And at those docks over there is where, during this project, where we had most of the earthen dam drained to allow for the construction of the spillway, we also took that opportunity to put in new inlet systems where we have new penetrations through the earthen dam and new piping that takes the raw water into the filtration system. The new intake structures allow us to take off water at stratified layers. Therefore, we can optimize the quality of raw water coming into the plant. The old system didn't give that ability. Therefore, we really had no control over the raw water intake from the Indian Brook, and that compromised us to some extent because we would bring in solids and raw water quality that is a little tougher to treat, more expensive to treat. So at the end of the day, we will get a return on our investment redoing the intake structures at the same time that we did the spillway. So all in all, between the spillway, the reconstruction of the riprap sidewalls that you saw there when you panned over the intake structure, and then the intake structure itself, and I'm going to have to pan around again all the way to that concrete structure just to the left of the red gatehouse. You could see the valve system there that controls our intake structure. So that valve system, the intake structure, the construction of the new riprap and core wall system, and the new weir plates behind us was a capital project that was completed a couple of months ago, and between soft cost and bricks and mortar costs, it cost the water fund approximately $4 million, but well worth it, and we believe we're going to see an ROI on that in less than 10 years because of the raw water intake that we're allowed to draw from this reservoir now. That will allow us to take less water from New York City. This water is for free. New York City water we pay for. So the more water and the higher quality water we can take out of this Indian Brook Reservoir is really a cost savings measure at the end of the day. From here now, we're going to go from...
I just have one question. I do have one question for you. So let's talk about the construction of this earthen dam. Excuse me. Let's talk about the construction of this earthen dam. When you started, you had to lower the reservoir. For us lay people, you had to lower the reservoir, okay? You had to buy your water from New York City because we had to continue to supply water to the residents of Ossining. And then you had this, the dam done and the riprap done and all your little other jobs that you had done underneath so that you can get water much more easier to the filtration plant. What was the time frame of that whole project?
From beginning to end, from commencement of construction to substantial completion, was approximately 1 year. It was done under the auspices of the DEC, who's our regulator for our water system, and we also needed to work around certain aquatic constraints that we had here for some of the life in and around the reservoir. We drained the reservoir at a time when some of the biology around the reservoir was least impacted, like the turtles and the salamanders and what have you. We also worked around the fish in the reservoir, where when we did drain the 100 million gallons down to less than 20 million gallons, we provided oxygen to those fish and fed those fish to keep the fish population intact. When we brought the reservoir back up, again under the eye of the DEC, we monitored the fish all along, and we're monitoring them now, where we actually, with the DEC's oversight, provided some feeder fish to feed the population that was maybe a little neglected for the 1 year of construction, and everything seemed to work out pretty well. We noticed no fish kills, which is that was the intent, and we did that successfully, and we're right back to where we should be with regard to the life inside our natural resource here. Christina at GoTV dropped this video in that we took earlier in the construction phase, where you could see the reservoir holding less than 20 million gallons at its deepest point to maintain aquatic life. Here you can see the intake structure at the far end of the video here, the new riprap at the crest of the earthen dam, and now our last piece is the serpentine weir system, which allowed for the increased surface area and increased overflow rates through our new spillway.
Here we are at the pre-oxidation tanks with Andy Teese, who's the water superintendent here in Ossining. So Andy, why don't you tell us a little bit about what we're looking at here?
Thanks, Sue. Essentially what we're looking at, we're going to start as a drop of water and work our way through the plant. We just talked about the intake structure and the dam and the reservoir itself proper. Now what you're looking at is the pre-oxidation tanks. So the water works its way through the dam, and we blend it with New York City Croton water. We're the only one on the old Croton Aqueduct, and it blends in the tank where you see the purple water down where you're panning right now. Basically, what we add is potassium permanganate, KMnO4, which allows us to oxidize any iron and manganese that's present in the water. So those are metals that you're oxidizing out. And I would say 12, 13 years ago, we put this system online. It was designed in the original 1986 plant. It was a chemical feed system, and we used to get quite a bit of dirty water calls. And what happened in the past would be that the iron and manganese would work its way through the plant, microscopically, soluble, and as soon as the chlorine reacted with those metals, it would turn brown. So you get quite a few brown water calls. So what we're doing here is we're oxidizing the iron and manganese in these pre-oxidation tanks so that it makes it into a particle that we can filter. That's the key. You need to filter out those two products before it works its way into the system. So we dose potassium permanganate, and as you pan through the tank, you can tell it turns from a purple color to a brown color, and that shows the demand of the system. That's what's being used up. So there's definitely a demand on iron and manganese, and the next process under that green shed dormer is our flash mixer. So essentially what we're going to be doing is we're going to take this water, it's going to have a detention time of about 4 hours, it's going to work its way into this flash mixer, which is essentially like a big mixer, and we add a coagulant. And what a coagulant is it changes the charge of the water. The water is negatively charged, we add a positive chemical, opposites attract, and we're looking to make a particle so that we can settle out organics, turbidity. Turbidity is the clarity of the water, so it would be essentially dirt, so that you're looking to remove these organics and turbidity before it works its way through the filters. So you're trying to, the plant is designed as a barrier method. It's designed sequentially, so you make the water better as it goes, so that there's less loading rates on our filters, which means gives you longer run times so you don't have to backwash constantly. We will then go through each one of those processes.
So in layman's terms a little bit, the water starts here, you put some chemicals in it so that you can take out other like iron and manganese. And as it goes through these little channels here, it gets cleaner and cleaner and cleaner. So that when it finally goes through the filter plant, it has the least amount in it so the filters can be used for a much longer period of time.
Correct. And also it makes it into a particle that cannot make its way through the filter. Before it would work its way through the filter as a soluble mix. Now it's a particle that the filter can catch, so you don't have issues in the distribution system.
Great. Thank you, Andy, and let's continue on.
Right now, Catherine is zoomed into the original 1889 gatehouse associated with the earthen dam. The earthen dam was also constructed at the same time as the gatehouse in the late 1800s, and this work that we just discussed earlier in the video with regard to the spillway and the intake structures is the first significant work that's been accomplished on this earthen dam since that time. So obviously, based on how we described it above, it was a much needed improvement, but this gatehouse, prior to constructing the new inlet chamber, which we also discussed earlier in the video, was the original house for the original earthen dam penetrations that provided the intake structure for the original plant. So we're going to maintain this gatehouse because of its historical significance, and that's about it. We're going to walk inside the plant now.
we're walking to our next process. We're in an air structure. Basically, this air structure was installed probably 8 or 9 years ago to protect the processes, the tanks from freezing and from organics. This air structure was put up for a little over $250,000, and it covers all the outside processes. As we walk down towards your left, the water works its way from the pre-oxidation tanks into these flocculators. As you see, these are they were installed in 1986. It's agitation arms with boards on them that work their way up and down. And for mixing energies, as I'd mentioned earlier, we add the polyaluminum chloride, the positive chemical, so that we can agitate it and make it into a flocculation particle. What it is it's the process of coagulation and the process of the charged particle, and you're trying to develop that particle into a larger particle that can be settled. We'll walk down towards the light at the end of this tank, and you'll see the variance in the flock size. We'll get a shot on that. So as you look towards your right, watch your step. If you could pan down to the bottom of this tank towards that light. And you can see the variance in the size of the flock particles. What you really are looking at as an operator to make sure you can see the clarity between the flock and the clear water. It's one of our judgment calls. We measure the streaming current, the actual charge of the water. We measure the flock particle size. We have an instrument down at the end of this tank that we're going to show you that was developed here that we can actually trend the particle size, so we know that if we had lost chemical or if there was an issue, the operator should look to make sure that everything is feeding correctly. They do every 4 hours, but it's more of belt and suspenders. Okay, we're looking in one of the flock basins, and what you see is a device that is an actual camera that measures, it actually sends information back to a computer, and it delineates the particle size, the density of the particle. This is the first one developed in the world. We started it here, and it's kind of a prototype. What we're looking at is something that would notify the operators on our computer system that if there was a change or something was out of whack, they could see it immediately. If you pan towards the computer here in front of you, you could actually see the trends of how the water flows through the plant and how the flock particle changes in size and density. Pretty proud of this system. I'm sure this will be used worldwide in the next 10 years.
Okay, so we just left the flocculation tanks where the flock is formed prior to flowing hydraulically to the sedimentation basins. Now, if you do a quick pan over to the flock tanks, just to give the viewers a general idea of the size of the flock tanks, and then you pan back to the 3 sedimentation tanks, you can see not only in depth, but there is a significant surface area and overall tankage size difference in the sedimentation basin. The sedimentation basins are much larger. If you picture a drop of water flowing from the beginning of the flock tanks to the end of the flock tanks, that drop of water takes about 45 minutes to fully flow through that tank, as opposed to a drop of water flowing from the inlet to the outlet in the sedimentation basins. That would take about 3 hours. So hydraulically, this is a much larger system. And what that allows to happen is the flock that forms in the flocculation tanks, if you want to get a little closer over here and pan down into the sedimentation basins, the flock particles that form in the flocculator tanks are discharged into the sedimentation basins, and essentially the water in which those flock particles exist slows down. The flow of that water slows down. And when a newly formed heavy particle is introduced to a tank where the flow is slowed, it settles. And that settled particle matter that takes out the contaminants that were originally in the raw water source, that settles to the bottom of these sedimentation basins, hence the name. The particulate matter at the bottom of the basins is what we call our sludge. And in our situation, we call it our alum sludge because of the coagulant addition of alum into the raw water that allows for the particulate matter to form. So that alum sludge is collected, and we're going to get that later in the tour. That's collected at the underneath these tanks with the mechanical systems that we have in the basement, and that is trucked off-site for potential beneficial reuse from a secondary hauler. The clarified water from these sedimentation basins flows into the last part of our treatment process, which Andy is going to discuss with you next, those being the dual media, anthracite, and sand filters. That essentially is a final polishing treatment of the clarified water at its sedimentation basins. Right now, Catherine is zooming in on one of the many cards of thanks given to our chief filter plant operator, Stephen Ho, for the tours that he offers here at the plant. One of the things that we started doing here at the plant when we finished with the renovations of all of our mechanical systems was to start doing public outreach. And our public outreach consisted of really young children and groups like the Girl Scouts and Boy Scouts, which you're panned in on now. And I'll ask you to pan over to the right over here, and you'll see some of the informational brochures that we have out here, some of the educational brochures that we have out here for our visitors. And one of the other pictures that we have up here that you're getting to on the right is another program that we started in connection with the outreach, and that was college internships. So every year for the last 5 years, we've had at least 2 college students, undergraduate students, that are primarily in the STEM field, are the sciences, that are looking for quality internship opportunities for their resume and for their overall educational experience, coming here and helping our chief filter plant operator. And they are interns that not only get a chance to see what potable water treatment is all about if they decide to maybe venture further into that field of study, but they also provide a true service to the chief filter plant operator by assisting him in the lab or some of the analysis of the plant as the water flows through the plant every day, because it's constantly tested and monitored, and these students participate in that effort under the direction of the chief filter plant operator. So the work at the plant has a lot of collateral benefits, and we're proud of that. And you can see a lot of the educational notes that we have posted up all throughout the plant for every component of the plant that really allows for layman's terms for a lot of the treatment processes that take place. And it's nice to see so much interest in this field, because it's not going away. Quality potable water is gonna be a constant need, and as we continue with development and a thriving economy in our village, this is definitely paramount.
Okay, we're at our final process. It's the filters. We have 5 filters, dual media. So after our sedimentation process, the water gravity feeds to these filters. The filters themselves, we have 5 in service. Essentially, there was 4 designed for the filter plant, and the 5th one was a pilot filter to be used as a testing filter for the future. But as the demand has picked up in the system, population increase, capacity, future capacity, we put the fifth filter online. I believe it was 2008, we performed a filter upgrade in which we, if you pan to your right, we changed the underdrain system. This is an underdrain system. Originally back in the 1940s when the first plant was put online, these first filters, it was a clay tile. And a lot of the clay tiles, it started to crack on top, and then you would get migration of water through, and it would allow for the easiest path. And sometimes it was easier than actually going through the filter media. So what we did was we took individual filters offline. We took it out of service. We installed this type of an underdrain system. It's Leopold. It's the manufacturer. It's a replacement in kind, but it's newer technology. So the water goes through here, through this center area. And normally what used to happen is, so on the old filters, we would have the clay tiles, we'd have gravel, then we'd have sand, and then we have anthracite on top of that. What we have here is the same setup, but this is what's known as an Ims Cap. This would be in place of gravel. But what happened in other plants out in the United States, when it was installed, there was issues with iron and manganese actually clogging this up, and they had issues with getting water through. We went with conventional gravel, sand, and anthracite, so we wouldn't have that issue. The advantage of this is it uses less freeboard area, and you could put more media on top, but it was it's worked out great for us. The other thing is the old filters had what was known as a wash system. It was like an arm that used to spin around and wash the top of the filters, and it wouldn't get through the media, through all the anthracite. You got to remember, you had like 12 inches of sand, 12 inches of gravel, and on top of that you have your anthracite, which is 2 feet, which is coal, it's carbon. What we do is we introduce air. This is an air scour backwash setup in which air gets pumped into this. After the filter is isolated, air would be pumped in. You would see your filter media raise because it was almost like a jacuzzi action, and then after it raised, the dirty water would work its way into the troughs. I'll look to see if we can do a backwash now by the end of this tour, so you can get a full idea of what happens here. So it's the final process before we add lime for pH control and chlorine for disinfection. But I want to show you some of the chemical feed systems that we built in-house after this. One quick view, let's just look into the filter itself. If you look over this railing, you can see all the piping that was changed and modified. This is the air piping, the stainless steel piping that pumps the air down into the filters when we do the backwash, and those are your filters. They're pretty small filters, but adequate enough for this size plant. Okay, so right now we are just started our air scour, and you can see the media is starting to boil, not actually by temperature, but just by velocity. This will happen for a couple of minutes, and you can see all the organics and everything that's been filtered through the system, the iron, the manganese, the turbidity, is starting to mix up. So after a certain time period, the air scour will shut down, and we will introduce our water so that we can flush these filters out. And the control strategy is it's kind of operator judgment call, but it's automated. And as the density of the water changes, because the temperature changes through the year, we adjust our profile of this backwash. Okay. Now you could just heard that the air scour shut off, and we're actually going to waste right now. So we have essentially 2,000 gallons a minute flushing through this filter media. It'll work its way up to over 3,000 gallons a minute. And you can see the dirty water that's working its way into the troughs. Now where that water goes is to our surge tank, and that's the water I talked about that would run through the thickener system, and we would remove the turbidity, and clean water would go back to the head of the plant instead of going to the sewage treatment plant. You could see it's quite muddy. We're getting close to 60 hours of runtime on our filters. That's a long amount of runtimes between backwashes. It shows that the process is optimum. Years ago, before these processes were changed, the operators would get 4 to 5 hours. So essentially they were running around like crazy trying to backwash these filters to make sure everything stayed in compliance. So it's a lot easier now. We're going to go to the next process, but you can see the water is cleaning up. You can see it's starting to look clearer in the center of the tank. You can see the delineation between the turbid water and the clean water. And when it gets totally clean is when the backwash valve shuts, and we will go to the next process of this control strategy, in which we filter to waste. We essentially put the filter online and we run it to waste for about 20 minutes, so that if anything's in the filter, it'll work its way back to the same tank. And once the numbers are safe and the turbidity is less than 0.1 NTU, we then put the filter online. You can see the difference in the water right now. If you look into the troughs, how clear it is. So it's pretty optimum the way this control strategy is set up. Okay, we're going to go into a little bit of our chemical feed systems. We're pretty proud of this. If you look to your left at the pumps on the wall and all the piping, all this equipment was installed in-house by our operators. One of our senior operators who retired 2 years ago. And it's really it's nice to have the bench strength in-house, that if there's an issue, we can fix it ourselves 99% of the time. And as you see, there's 3 pumps on the wall, and as you come this way, you can see the pump on the right is running and the other 2 are offline. We always try and keep 2 as a backup in case there's an emergency situation. A pump clogs, a part fails, you can immediately put the other pump online and still have a backup while you fix it. So this is a sodium hypo system. It's used for disinfection. We add some chlorine on top of our filters. It helps with anything that the pre-oxidation tanks didn't oxidize out. So after the sedimentation tanks that you see that Paul just talked about, before filtration, just a little bit of chlorine gets added on top, and it makes a huge difference with what happens with oxidation. As we walk down this chemical feed area, we have filter aid polymer systems. These are basically that if we get into unknown waters, if we get high turbidity and we need to help with the coagulation process, we have systems that we built in-house here that we can energize immediately to help with the coagulation and settling of particles. As we walk down to the end of this hallway, this is the permanganate system that we talked about for oxidizing the iron and manganese. These systems were built in-house. The old system used to be a dry feed system, and it was not the most reliable system. This is actually very reliable, because what an operator will do is manually add the chemical themselves, and they'll weigh it out on a scale. They'll put it into this day tank, and they'll look to see, based on the pounds, how much water should be added. It's foolproof. We made it simple. We have operators here 24/7, so it's the right thing to do. Okay, what we're looking at here is we use this for our tours, And also the chief operator is based out in the hallway area, so he can keep an eye on things all the time. This is our SCADA system, Supervisory Control and Data Acquisition System. Basically, it allows you to point and click and to operate the whole filtration plant from anywhere between this office, the office that we're going to show, the old control room, downstairs if there's a catastrophe, if there was a major fire in the plant or something unforeseen. There's 3 locations. It's very important. So an actual overview of the plant, let's talk about that real quick. We talked about our Indian Brook Reservoir, which I'm pointing to on the left-hand side. We take water from our Croton Aqueduct, and we pump it, and it mixes in our pre-oxidation tanks that we looked at where the purple chemical was, actually here. Then we have our rapid mix, in which the water has the polyluminal chloride added, becomes positively charged. We have our flock basins that the particle builds up into a larger particle. Then our sedimentation basins where the water was stayed in there for detention time of 3 hours. And then our filters we just talked about. We add lime, and we add fluoride, and we add chlorine for final treatment. So that gives you an idea of what's going on there. Now, when we backwash our water, the dirty water goes into these holding tanks, which is important. And what we do is we run it through this thickener system, which we'll show you, and it removes the solids, and the clean water that's drawn off the top then works its way back here to the head of the plant. Now that's key. That was about $300,000 a year of purchased water that we used to just send down to the sewer plant, the county sewer plant. But now we recycle it back to the head of the plant for the last 10 years. That adds up. That's $3 million of purchased water in 10 years. And from this point forward, that's the way it'll be. We just asked for authorization from Westchester County. We proved to them that the water was safe to be recycled back. And the sludge that comes off those surge tanks and the thickener, they go out to our sludge holding tank, which is down here, and that's what gets hauled off. I'm going to show you the operator control room, the new versus the old, and we'll go from there. Okay, so we're in the control room. To the left, if you pan to the left, you can see the old 1986 control strategies that were set up. They were just manually on-off pumps, push-button type setups. It was okay for that time period, but as the regulations have changed from the Safe Drinking Water Act and from 1993 on, the regs have gotten stricter. And in order to perform or to actually process clean water to the best of your ability, it's not optimum to just start and stop pumps. We're going to talk about that with our VFDs, our variable frequency drives that we installed to keep this plant running at a steady state instead of more of a pump station on-off setup. You can see the old alarms that were up here, that's all the operators really had. That a filter shut down or there was a utility failure, or if a day tank was low, that's where, like the process chemicals. Here on our new setup, the new supervisory control data acquisition, it's not new, but it's new to the public. It was installed about 7-8 years ago. And what we have the ability to do is control anything from anywhere in the plant. I showed you out in the main entranceway. This is one of the screens. We're talking about, we just initiated a backwash, and it's key because this actually goes through the process of how valves are controlled and to what levels they open, and this is the whole control strategy, and the filter's automatically doing that. But the operators have to understand how to do that. If there was a failure of the SCADA system, you still need to know you need to manually open and close valves. The one thing that when we upgraded the filters, we changed it. It used to be water-operated valves, and if there was a water main break in the driveway or if there was a low-pressure situation, here you are trying to operate a filter plant, and you couldn't control your valves. What we have the ability now is we put electronic valves in, and then we control it from this location. We're getting a view of our variable frequency drives. Those are those big units that we talked about. That controls the speed of the pumps. I consider this one of the best upgrades to this filter plant. Gives us the ability to control the speed, and if we can control the speed, we could save lots of money on the electrical savings. Also gives us the ability to run steady state and to match our flow within 100,000 gallons a day. running from 2 MGD to 4 MGD in the old days, it wasn't easy. Now we can match it exactly. If you pan to our right, we're going to look at our thickener system. Now this system was put online probably about 12 years ago, and we had to prove to the health department that it was safe for the water to go back to the head of the plant, and I want to show you as you walk up here what I'm talking about. That allows us to take the backwash water. You just saw the backwash, and all that dirty water that was extremely turbid and dark, we run it through this system, and we allow the sludge to settle to the bottom of this tank. The clean water that's coming off the top here, which equates to about $300,000 worth of purchase water a year. If you look down into the tank itself, you can see that that pipe allows it to go back to the head of the plant. That used to go directly to the sanitary sewer, and now it doesn't. So you can see that what's going back is safe and it's treatable. There's no reason why we shouldn't be sending it back.
One of the last stops we're going to make on our tour here is inside our lab. With us inside the lab right now is our Chief Filter Plant Operator, Stephen Ho. I'm going to let him talk a little bit about the work, but before we do that, I want to let the audience know that one of the advantages of having a New York State certified lab under the regulatory oversight of the county and state departments of health is that any of the testing that is required by our regulators for our potable water plant is all done here in-house. In addition to that, any of the testing that's required by the distribution personnel when there's a water main break or a new water main installed is also done at our New York State certified lab right here at the Indian Brook potable water filtration facility. So it's really one-stop shopping here for all your water needs, if you will. And Steve works in conjunction with the distribution folks all day out there in the village. So I know Andy talked a little bit earlier about the SCADA system and how from an instrumentation perspective and a data perspective, our distribution system out there throughout the village and the town is all tied back into the plant. But they really do run in concert, and there's not only a digital connection, but a chief filter plant operator out to the distribution foreman, to the water superintendent, Andrew Teese connection all day, every day, 365 days a year. So that really has a lot of checks and balances within our system. So if something goes wrong in one area, you have other areas watching the same. So they all really work in concert every day. And to talk a little bit more about the specifics of the lab and some of the tests that we do on a daily, monthly, and yearly basis, I'm going to turn it over now to our Chief Filter Plant Operator, Stephen Ho.
Thank you. So along with all the online meters throughout the plant, we take tests every 4 hours. So every meter that you see through the plant, we actually do bench tests. And the bench tests are really what we go by. The online meters are for convenience, but we, every 4 hours, do all those tests to make sure the online meters are working and are accurate. Every day we check for bacteria, total coliforms, and E. coli here at the plant and also out in the distribution system. It's required by the health department, and all those records are reported to the state every month. So part of being an operator here is the test and the laboratory work. It's extremely important, and that really tells the whole story on how we're doing, how the process is working throughout the plant. And you know, we're very proud of our plant. We're regulated by the state. We're audited every 2 years on our techniques, and every operator has to take a lab course to make sure that they're in tune with any new techniques, things like that. That's about it. Yeah, so if you went through the plant, the whole process, a major part of the process of treating water is removing the impurities. The first major part of that is coagulation process, where we use a coagulant. It's an aluminum product, and in order to figure out the dosage, we have this instrument over here. It's called a jar tester. So it's a seasonal variation with the raw water, dealing with temperatures and things like that. So we are constantly doing jar tests to simulate the process through the plant, the dosage of the plant. This instrument here allows us to simulate the treatment process and to better determine the dosage rates of the coagulant. So it's a very important piece of equipment. It's called a jar tester. Every operator is trained to use this instrument. That's a bit. Oh, and then over here, you'll see plenty of bench instruments. This is a spectrophotometer. Okay, we're able to do many inorganic chemical tests with this: free chlorine, total chlorine, manganese, fluoride, to just name a few. This here is also a very important instrument. This is a turbidimeter. It measures the clarity of the water. Okay, we do a lot of turbidity tests. If you go around here, we have our pH meter right here. And then this is our TDS meter, total dissolved solids, and on the end is alkalinity. All these instruments and tests are used to determine things like our corrosion control program, so we're protecting the pipes from heavy metals, things like that. So we're doing these tests every day of the year.